Good morning, Physics 20. I hope you guys are having a good day so far. Guess what? This is the very last of the Physics 20 physics videos. Can you guys believe it? Already? I know, this year's has gone by fast in spite of COVID, I will admit. So, ladies and gentlemen, today we're going to be looking at the Doppler effect. I hope you guys enjoy the meme from our very friendly and popular TV show there. So, ladies and gentlemen, essentially what the Doppler effect is, it's how the sound waves change because of an object that is moving. And as we're going to look at a little bit next year in Physics 30, it's not just sound waves that change because of this, it's all waves that change when an object moves. And it has to do with the compression or stretching out of these waves because of that object's movement. So therefore, an individual who hears the siren of a, fire truck going by, it's going to sound different if you're standing on the sidewalk here, when the fire truck is here, or when the fire truck's over there as it drives past you. All right? Okay. So, ladies and gentlemen, let us begin. So, what we've got is, now once again, the sound is going to change as your siren goes past. However, we're not talking about the volume, okay? This has nothing to do with the volume. It has to do with everything in pitch. The Doppler effect itself has nothing to do with volume, okay? The only reason why an object may sound louder to you while it's farther away is because it's farther away. The fact it's moving does not change its volume, okay? So a change in pitch is a change in the frequency of the sound, okay? So if a source is going to be moving closer to you, the pitch is going to sound higher, okay? The frequency is going to increase. However, when it's moving away from you, the pitch or the frequency of the source is going to seem to decrease. So what causes that is because of the compression or stretching out of the sound waves. So, as we have our lovely motorcyclist here, sound of spring in Grand Prairie. Brah, brah. Right? Well, the motorcycle's finally coming out from all the winter. So these circles represent the peaks of the sound waves. So the areas where the particles are the most dense, because remember how our sound waves are longitudinal waves, not transverse, they're longitudinal, compression and relaxation essentially. So these are the peaks, okay, and then the gaps are the troughs. Well, notice behind the cyclist that gap between these wavelengths is increasing. Notice in front, these sound waves are compressed, okay? So if our motion is this way, we'll call this one observer number 2. We'll say this one's number 1. And here, because our source is moving towards, our sound waves, so lambda, is going to be compressed, okay? It's going to be scrunched up, okay? So that means lambda is going to be shorter. Now remember, ladies and gentlemen, that if our speed of sound doesn't change here, okay, when we have this equation, we have your frequency is inversely proportionate to your wavelength. So that would mean, therefore, our frequency is going to increase. So we decrease this one, this guy's going to increase because they're inversely proportionate. Okay, so let's think about observer number 2. Let's look at these wavelengths. Okay, here our source is going to move away. All right. Notice how lambda, your wavelength, is going to be stretched. Okay, your sound waves are completely stretched out there. And that means your lambda has increased from what it was. Now, same equation that we looked at over here, because our wavelength and frequency are inversely proportionate to each other, okay? Well, you increase one, you're going to decrease the other, okay? So that would mean, so therefore, our frequency is going to be decreased. All right? Okay. So, ladies and gentlemen, let us begin with some calculations in our lovely equations. So here, ladies and gentlemen, what this is called, when the frequency of a sound is changed because it's moving, so the observer is going to hear something different than what it actually is, it's called our Doppler effect. So that's the change in the observed frequency to someone who is the object moving past them. So ladies and gentlemen, the apparent frequency that an observer can hear of a moving object, so not the frequency of the actual source, what the viewer hears, is determined by this equation. This is on your data sheet. You can find this Doppler effect equation right here. On your, right there. Yeah, right there. On your data sheet. Okay. So, now this is a bit tricky because we have 3 V's and 2 F's in the equation. That makes this a really tricky formula. So you need to just really take your time with it and really make sure that you're aware of which F and which V means what. So just plain old F is the apparent frequency that the observer is going to hear. So when we say apparent, that's not the frequency that the object is actually releasing with its sound. That is what this guy here or this guy here are going to actually be hearing. Okay? So Fs is the true frequency of the source. So S is the source. Okay, that's what that means there. Okay? And that's the source of the sound. So that would be the motorcycle in the image above, the frequency that the sound of that engine is releasing. V is the speed of the sound waves. Now this is the confusing part. And Vs is the speed of the source relative to the observer. That is the tricky part. The lowercase s, ladies and gentlemen, equals source. Okay, so this is the speed of the source, and this is the frequency of the source. The V without the S is the speed of sound. Okay, I know that's really confusing. I'm sorry, it's a bit of a pain in the butt. That's what we got. So what I would do is on your data sheet, write that down. Write this stuff on your data sheet right underneath that formula, and you even have a space right under here to write all that stuff down. Sounds good? Okay. Now notice here, this has a plus minus sign. What that means is you're either going to be adding or you're going to be subtracting here. Okay. Now the tricky part of this is you're just going to have to memorize it and write this on your data sheet. So you are going to use the plus sign convention if the source of your sound is moving away from the observer. Okay. And you're going to use the minus, so you'd use the negative if the source of the sound is moving towards. Okay, so ladies and gentlemen, I don't have any fancy way for you guys to remember this. You're just gonna have to memorize it. Write it on your data sheet, memorize it, you're good to go. All right? Okay. So, ladies and gentlemen, let's do a couple practice problems. So, a whistle with a frequency of that many hertz. Okay, pause. We have a whistle with a frequency of this. What frequency is this? The frequency of the source? Or is this the apparent frequency the observer's hearing? Frequency of the source. It says a whistle has this many hertz. Okay, so that means our Fs is 965 hertz. Is moving with a speed of 23 meters per second towards a stationary observer. Okay, pause. Moving at a speed. The whistle is moving. The whistle is the source of the sound. So therefore, yes, speed of source. So 23 meters per second. If the speed of sound is this, so remember plain old v is the speed of sound, so 342 meters per second, what is the apparent frequency of the sound heard by the observer? Okay, so ladies and gentlemen, fortunately for us, we don't have to rearrange this guy. So we have our equation is F is equal to our V divided by V plus minus our V source, and that is multiplied by the V source. Ladies and gentlemen, well, what do I use? Do I use the plus or the negative? And how do I know? What keyword have I not underlined here? Toward. Ladies and gentlemen, that keyword toward, what does that tell us we need to use? Positive or negative? Negative. Okay? So that means you need to use the negative sign. Okay? All right. Have I told you guys why I obsessed with circling my pluses and my negatives? It comes from organic chem back in university well over 10 years ago now. I had a prof who would deduct points if you did not circle your charges on your 3D chemical drawings. So, and I was so paranoid of this that to this day, well over 10 years later, I still panic about possibly losing grades if I don't circle my positives and negatives. Isn't that funny? Yeah, I think it's funny. Okay, so ladies and gentlemen, we are then going to use our V as equal to V over V minus Vs. So because we're moving towards, we're going to use that negative sign. Okay. So this is the equation we're going to use. All right. So now we're going to take our V, which is the speed of sound, so 342, and we are going to divide that by your 342 minus 23 brackets. And then we are going to multiply that by our 965 hertz. Okay. So ladies and gentlemen, this is going to be a bit of a pain in the butt to put in your calculators. Okay. So what I would do if I was you is I would go this minus this. So 234 minus 23, enter. 234 divided by second answer, enter. Times 965, enter. Okay? So by putting it in that order, you are not going to get your bed mass wrecked. All right? Because remember, this dividing line, that has to be done last. It is assumed that everything on the top is in brackets and everything in the bottom is in brackets. So that has to be done last. Okay? And then because this whole kit and caboodle is in brackets, then it has to be multiplied by this at the end. Okay? So watch your bed mass rules on this guy when you're putting this in your calculator. What you're going to get out of this in your calculator, that is the messiest 5 I have written all day. There we go. That's what you're going to get in your calculator. And with lovely sig digs and units, you go back to the question. 23 meters per second is 2 sig digs. So I need to round this to 1.0 times 10 to the power. I've nearly wrote units as an exponent. Yeah, man. There you go, computer. 3 hertz. Sounds good, guys? Okie dokie. So we're on to our next question here. Question number 2. Good morning again. We're back and I broke the internet again. It's what I do. So let's get on with number 2. I'm a poet and I didn't know it. All right. So ladies and gentlemen, an ambulance is driving away from the accident at 27 meters per second. So key word, driving away. What does the word away tell us with the Doppler effect? Positive. That means we have to use the positive in that equation. So it's driving away from an accident at 27 meters per second. Okay, now is this V or VS? VS. The reason why, ladies and gentlemen, is because that is the speed of the source and the ambulance is the speed of the source. Okay, so 27 meters per second. A witness at the scene hears a frequency of this many hertz. Okay, that's the key. This is the observer. So that means this is just plain old F. That is what this observer hears. If the speed of sound is this, okay, now remember, plain old V, because Vs is speed of the source. So plain old V is the speed of sound. What is the true frequency of the ambulance's sirens? Okay, so that is Fs that we are trying to solve for. Okay, all right. So let's write out our equation. So our V over V plus minus Vs, brackets, multiplied by Fs. Okay, this is positive because we need to, because of the keyword away, so we're going to rewrite this. So our frequency is V divided by V plus Vs, brackets, times Fs. We are trying to find Fs here. So what would I do with this? How would I rearrange this? Divide by this stuff. Don't bother trying to break this apart and move it piece by piece. I mean, you could if you wanted to. It would be a pain in the butt. But you might as well just move this all over as one chunk. So I'm going to divide both sides by V over V plus Vs. So Fs is going to equal my F divided by my V divided by V plus Vs. Okay, it's messy, I know, but it works. So, ladies and gentlemen, for this guy, we're now going to plonk our numbers in. Our frequency of 872 hertz. Well, this is where it's going to become a bit messy on the writing it down. Okay, so the V, so your speed of sound is 344 meters per second. And we're going to divide that by 344 plus 27 meters per second. Okay, now putting this in your calculator is certainly going to be a bit of a pain in the butt. Okay, but take your time, really think about it, and solve this first. 349 plus 27, enter. 344 divided by second answer, enter. 872 divided by second answer, enter. Okay? Okay. So then what we're going to do is once that's plunked appropriately into your calculator, you are going to get 940.44 ... hertz. All right. Sig digs, ladies and gentlemen. are what? Come on, how many sig digs? 3. Because I gave you 3 sig digs, I want this rounded to 940. Units are hertz. Identify your answer, and we're done. So, ladies and gentlemen, what we've got here is your practice problems for this topic. Give some of those a shot. They're in your data booklet. And with that, we end the last lesson on Physics 20. Time has gone by fast. It's nuts. I know. So, hope you guys have a good summer, and we will see you guys all next year in grade 12. No fires, injuries, or explosions. We will talk to you later. Now I can't turn this thing off. I keep breaking the internet. Bye, guys.